Hello, everyone. We are Group 2 in ME 157 presenting our product, Energy Efficient Smart Window Blinds. I'm Rafael Salvo.
I'm Daniel Hernandez.
I'm Arthur Garcia.
I'm John Marambira.
Why smart window blinds? With people being more comfortable working from home or those interested in building a smart network in their house, the window should be among the first to be integrated to improve daily life. Smart window blinds that can slow down change in temperature and can open or close at set times. Blinds that can function simultaneously with other smart devices and close if something is approaching the window. Blinds have been made with many different materials, from wood, plastic, vinyl, and aluminum. We chose a thermoplastic, PVC, as our main material for the blinds. We have more freedom in our design than if we were to use wood. Its durability, though not comparable to aluminum, is enough for blocking sunlight. Being a more affordable material as well, we can design for modularity and replacement of parts. The mechanism we chose is a rack and pinion. Both pinion and spur gear are made of AISI 4030 steel. Being the load-bearing joint, having over 10 times the yield strength of PVC, this steel is more than enough. This would benefit us when integrating modularity, as the main mechanism's longer expected product life promotes staying with the same manufacturer through replacement parts that are more appealing. Now with more, Daniel Hernandez.
Thank you, Rafael. So for the AISI 4030 steel spur gear, the properties we're going to mainly focus on are the ultimate strength at 81.2 KSI and the yield strength of 66.7 KSI respectively, which we use the yield strength directly to find our factor of safety at the end of our spur gear. So our entire smart blind system will be powered by a motor plugged into a wall at 12 volt, 2 amps, so 24 watt at six, and the actual gear will be spinning at 60 RPM. So first off, the assumptions we made for the spare gear is that it will be machined. The pressure angle is 20 degrees. It's going to have 20 teeth. It has a diametral pitch of 8 teeth per inch. We found a Fates width range of about 14 over diametral pitch, so about 1.75. Our Lewis form factor of 20 teeth ends up being 0.322, and a design safety factor of 2. With the power and RPM, we found our torque to be 33.81 inch-pounds, a pitch diameter of 2.5 inches, and a workload of 27 pounds. Our size factor, using range factors, is 0.842. Our equivalent diameter is about 1.1 inches. A size factor is 0.87. Our load and temperature factors are equal to 1. Our endurance factor, we felt that 90% reliability of the gear is appropriate for this, as the blind system is meant to be used over time. And a miscellaneous factor of 1, giving our total endurance limit to be 26.68 KSI. Afterwards, we found our geometry factor to be 0.35. We found our pitch line velocity equal to 39.27 feet per minute. Since we were assuming the spare gear is going to be machined, we went with a cut milled profile in customary. So our dynamic factor is going to be 1.03. Our overload factor is going to be 1.25, given that it's an electric motor and we feel like there could be moderate shock in the system. Using the AGMA equation, we found that the stress applied to the teeth of the gear should be 454 psi. Our root fillet radius is going to be 0.035 inches. The radius over pitch diameter is 0.15. So given some approximations, our big D over little d is 3, our KT is 1.68, and our Q is 0.62. With that, we could find our stress concentration factor, KF, equal to 1.42. Next, we find our allowable stress, which is endurance limit all over stress concentration factor times design safety factor, giving us an allowable stress of 9.39 kpsi. And using the allowable stress divided by the yield stress of the property, we find a factor of safety equal to 7.1. And with a higher factor of safety compared to our design factor, we find this very desirable in our design, as the actual margin of safety should be about 2.5.
So our mechanism comprises of 7 components, as shown on our bill of materials, which are 1 frame, 1 rack, 1 pinion, 1 3-inch linkage, 1 bar, 33 0.75-inch dowels, and lastly 31 blinds.
So I'll go ahead and I'll walk you through the final element analysis we performed to validate the structural performance of the smart window blind system. We focused on 2 critical components of the system, the linkage and the bar, both of which are made of rigid PVC. And our goal was to ensure these components could handle the applied forces safely and effectively. To begin, let's look at the mesh generated for these components. For the linkage, we used a medium mesh density. This resulted in a total of 13,858 nodes and 8,516 tetrahedron elements. The bar also was generated with a medium mesh density. This yielded 88,192 nodes and 50,617 elements. The medium density mesh allowed for a good balance between computational efficiency and accuracy. So now let's examine the loading and boundary conditions that were applied during the static analysis. We applied a hinge pin supports at the dowel connection points. This was used to replicate how the linkage and bar are secured in the assembly. Both the linkage and bar were subjected to a force of 15 pounds, and these conditions were used to represent typical operational forces the system would experience during use. So moving over to the results. This is the von Mises stress distribution for the linkage on the left. The maximum stress came out to 525.5 psi, which is far below the tensile strength of rigid PVC. And this shows that the linkage is well within its safety limits. The displacement indicates excellent rigidity and a negligible amount of deformation. So taking a look at the results for the bar, the maximum von Mises stress for the bar came out to 116.9 psi, which is again well within the material's strength limits, and the displacement confirms that the bar can maintain its structural integrity under the applied loads.
So in conclusion, I can say the results from the stress analysis show that both the linkage and the bar component exhibit a maximum value of von Mises stress that is below the tensile strength of rigid PVC, which is 4.6 times 10 to the power 7 Pascal, or approximately 6,672 psi. The linkage experienced a maximum stress of 5.255 times 10 to the power 2 psi. The bar experienced a maximum stress of 1.169 times 10 to the power 2 psi. Both values lie far below the tensile strength of the PVC material. Additionally, the maximum displacement indicates that there is excellent rigidity and minimal deformation when under the applied load of 15 pounds.